Welcome, dear listeners, to another exciting episode of Acadia's Ahead of the Curve. Today, we're going to talk about the ORE GPGPU project, which is running open source RISC engine on GPUs for improved performance. My name is Eric Ehlers. I work in expert services, and I'm joined by Jerry.
Hi, I am Zeyu Shen. My colleagues also call me Jerry. I'm a senior quant analyst in quant service. I'm based in Boston.
So the ORE GPGPU project, I'll just break that down. Normally, when you run calculations on your computer, they run on the CPU, which is the central processing unit. Going back 20 or 30 years, they've introduced graphics cards, which contain GPUs, which are graphical processing units. And of course, graphics cards were originally intended for graphics, but people very quickly realized that they could take other calculations and speed them up by running them on graphics cards. And that's how you got GPGPU, which is general purpose GPU programming. So the ORE GPGPU project is to take ORE RISC calculations and run them on graphics cards for improved performance. And the main motivation for this project is that we have some backtesting calculations which currently take several days to run, and we're trying to get that runtime down to a few hours. So there are multiple implementations of GPGPU available. One of them is CUDA. Do you want to tell us more about that?
Yeah, sure. CUDA is a platform developed by NVIDIA. So in CUDA, we refer to the CPU as the host, and we refer to the GPU as the device. So CUDA is basically a set of APIs that allows the CPU to interact with GPUs. So you can do a lot of things. For example, memory allocations on your device. You can do memory copies between your host and device. Also, you can just call kernels on your host. So CUDA also has many libraries, and some of them are pretty useful for derivative pricings. For example, the QRand libraries. It is used for generate random numbers, and it has many double-digit random number generators supported. For example, a quasi-random generator called Double Sequence, a pseudo-random generator called Mercenary Twisters. These two are very commonly used in the industry. And another pretty useful library is the cuBLAS library. It is normally used for linear algebras, so you can do, for example, matrix multiplication using it. So in CUDA, it is actually pretty easy to implement your own code to do the matrix multiplication. But when using the libraries, these codes are optimized at the compiler level, so you will see the performance to be much better when using these libraries comparing to your own code.
Thanks for that overview. So CUDA is a proprietary implementation for NVIDIA graphics cards. Another implementation of GPGPU is called OpenCL, which is a free open source implementation. So with OpenCL, you can have multiple builds. The first one is a base case where the code runs on your CPU, just like a vanilla build, so zero increase in performance. And then also with OpenCL, you can take an application like ORE, and you can run it on whichever graphics cards are available on your computer. So for example, on my work laptop, I have an Intel graphics card, I have an NVIDIA graphics card, and with OpenCL, I can run ORE on the CPU, on the Intel graphics card, on the NVIDIA graphics card, and I can compare those three implementations. I can benchmark them for performance and see what runs faster. And as I said, OpenCL is free and open source, and we already have an OpenCL implementation of ORE on GitHub. So anybody who's watching this podcast who might be interested in running ORE for GPGPU, there's a build already out there. and it's free, and you can install it and fire it up. We also have a tutorial in the pipeline, so hopefully by the time people see this podcast, the tutorial will be online, and that provides step-by-step instructions on how to run ORE using OpenCL. So this framework that we use to run ORE on GPGPU, that we use for OpenCL and that we use for CUDA, we call this the ORE GPGPU framework. Do you want to talk us through that in a little bit more detail?
Yeah, sure. So the framework is basically an outside layer to the ORE. So when we first start developing these frameworks, ORE at the time has like millions of lines of code. So we think it probably makes more sense to just develop something outside of ORE instead of changing all the code in the process to support GPUs, because otherwise it will be very time consuming and probably not even doable. Currently the framework is mainly used for scripted trades. So script trades are mostly using Monte Carlo simulations to do the pricing, and it is very slow, pretty slow compared to other trade types. It is one of the main bottlenecks of ORE. So when using the GPUs, we can just increase speed by a lot. And the Monte Carlo simulations, they're naturally like a large scale simple calculations, so they're just naturally suitable for GPU processing. And currently we support 3 frameworks in ORE. The first one is basic CPU, the second one is OpenCL framework, and the third one is the CUDA framework. The CUDA framework is currently under development. So for users, you can make your own choice of which framework you want to use in the pricing engine.xml. And when you select either CUDA or OpenCL framework, you can also specify which GPU you want the framework to be run on. So in the framework, we're also using the runtime compilers of the CUDA or OpenCL. The reason why we're using that is that, so for example, for static backtesting, it is basically we reprice the trades for when using historical data for like thousands of times. So we just build the kernels the first times we run those pricings, and then for the subsequent reprice of this trade, we just reuse that kernels, and it will be very efficient in that way. So for the ORE framework, we're also using the CUDA framework. We're also using Mercenary Twister, a random generator, which is it's a double-digit one, because according to what we have viewed in our testing, when using a single-digit precision random generators, the result can be 6 to 7% away from the result you get by using CPU.
So you highlighted a couple of important aspects of GPGPU programming. A graphics card, it was originally designed to run graphics, and it's optimized for graphics processing. So for example, you might take an image with 1 million pixels, and you might want to transform every single one of those pixels in the same way in parallel. So if you're going to take a financial application like ORE and run it on a GPU, it takes a lot of expertise to design that sort of implementation. You can't just take any part of ORE and run it on a GPU. So if you're just loading data from a database or something like that, that's not going to benefit from running on a GPU. You need to take a large number of similar transactions that you're going to run in parallel. And what you just described about, for example, taking a Monte Carlo analysis and running it on a GPU, that is the sort of calculation that can be perfectly optimized on a GPU. So far, we've been talking about running ORE GPGPU on, for example, a developer laptop. You can get much better performance by running it on high-end hardware. Do you want to talk a little bit about that?
Yeah, sure. Once we finish the development for the CUDA framework, our next step is to migrate that to the AWS. AWS stands for the Amazon Web Service. So the reason why we'll do that is because we can utilize A100 GPUs there. The A100 GPU is NVIDIA's latest GPUs. It has low latencies. It has a lot of tensor cores you can use to do the GPU processing. So we expect to see a huge performance boost after we migrate ORE to the cloud.
So in conclusion, the ORE GPGPU project, we already have the OpenCL implementation released as open source. We have a tutorial in the pipeline, and currently under development is the CUDA implementation, which will also be released open source, so anybody can download that and fire it up. And then internally, we're working on migrating that build onto Amazon Web Services, where we will run it on A100s for maximum performance. And our goal is to take our backtesting service and speed it up by orders of magnitude. Jerry, that was very interesting. Thank you very much.
Yeah, thank you for having me.
It's a pleasure. I hope you enjoyed this conversation as much as we did. Thank you very much for joining us. And if you would like to delve deeper into the topic of this podcast, then please visit us on acadia.inc.